Hi, so a few people have been having trouble with this homework, and hopefully you saw that I put this little chunk of it as bonus, but I'm going to solve one of these scenarios for you. And please let me know if you can give me like the exact problems that you're really struggling with. Just send over like a screenshot of where you're getting stuck. I can make a ton of more videos like this, so just let me know what you would like to see. Okay, so what I'm going to do is I'm going to take my snipping tool and just grab one of these scenarios. So I'll solve one of them. And you don't have to use Mathematica, but if you do use some kind of math software, MATLAB or Maple, or just whatever you're used to using, that would be really, really nice to be able to just copy and paste and get some of the different scenarios going for that. Okay, so let me go ahead and I'm going to open up a new notebook file here and just copy in the problem statement, and hopefully you'll see this is just kind of similar to almost seeing what I'm plugging into a calculator. Okay, so this is going to be, if you drew a free body diagram of the basketball, we're only under the influence of gravity here. So we're going to be using our constant acceleration equations. And let me see if I can draw with my mouse. So forgive my handwriting here. I'm trying to do this with my mouse. So we have some initial velocity going on, and we're going to split that velocity apart just like we would split forces apart. So here's the x and y components. We're given an angle over here, 30 degrees. So it looks like our x component is going to be the cosine chunk of this. And make sure you get the signs in here right. So we're going to be traveling to the left. Yeah, sorry for my handwriting. I'm trying to do this with my mouse. Okay, so if you get in our x and y components of velocity, and then we're going to write down those constant acceleration equations for the x and y directions. And depending on where our target is, so we're going to have some different values for those h and d of where the basket is. And we're supposed to try and match that up with our starting velocity and time. So we're going to solve for our V naught based on where our target is, where we are with respect to our target. Okay, so edit copy. Let me change this over here again with my notes. Okay, so to do this, I'm going to go ahead and clear out the starting velocity and time. Let me go ahead and zoom in on this so it can show up. If the videos are ever fuzzy, make sure the quality of the playback is set to high definition, so hopefully it's not fuzzy. Okay, so let's say we have some scenario. I can get this little math assistant up if you go to palettes, if you do happen to use Mathematica, and come by the lab or a lot of the universities. I think some of you are coming from Texas Tech and Lamar, and they should have Mathematica loaded in their computer labs. I think a few universities, actually, that's part of the free software you get as a student going there. So if you do want to use it, check out to see kind of what computer labs are near you and what resources they have over there. And the help for Mathematica is really great. You can type in anything you want to do, and it has examples you can copy and paste with. But yeah, here's the basic Math Assist palette, and that's where I have little templates for stuff. And you can do this by hand, and that's fine if you want to do it by hand, but it's really going to be a lot faster to crank through this stuff using some kind of software. Okay, so what do we have here? We've got our distance. D is used for derivative, so I'm going to call this dd instead of d. So if we're given our distance is 912, so it looks like feet. Ooh, so we're working in feet, not meters, so make sure all of our units correspond with that. So that means like our G is going to be 32.2, not 9.81. Let's see, what else are we given? So we have this distance, we have H, we have an angle of 30 degrees, and Mathematica likes to use radians. So let's go ahead and convert that degree. When I put a semicolon at the end, that's just going to suppress output. So I'm entering these function variables, but I don't want that to be outputted. Okay, and of course at the end, let me just put in those constant acceleration problems we're going to solve. So I have two equations I'm going to put in. So I have my square bracket that goes with the solve, and then I have a curly bracket that I'm going to put those two equations in and then two unknowns. So here we go. X is equal to, and it's a kind of a C++ thing to use two equal signs here. X naught, be careful, 0 versus O, plus V naught T, and it is case sensitive. So this is going to be the X component of our starting velocity. So if we look up here at our triangle, the X component, we're going to be actually going in the negative direction, traveling to the left, and that's going to be V naught cosine theta. And I'll go ahead and define everything up here. This will make it super easy in the future that I can change this angle, I can change what this is, and it will resolve it from all of my variables defined on top. So I'm going to keep it as a generic equation down below, and then define all my variables up here, and this will make it a lot faster too. Okay, so X direction, I don't have to worry about 1/2 AT squared. We have a constant velocity going on here, and then in my Y direction, I have whatever my starting position is, and then the Y component of my starting velocity, and we're going up, so we'll call that positive, and that is opposite that 30 degrees, so that is going to be our V naught sine theta t. And this time we do have gravity, and gravity's acting down, so I'll say minus 1, and I'm going to go ahead and use my template. I can just use a backslash for that too, but it's kind of nice to get that in a nice form there. 1/2 AT, and here's my squared. Okay, so there's my two constant acceleration problems. What's going on in the X direction, what's going on in the Y direction, and you'll notice those two are inside these curly brackets. And now I am going to do a comma, and inside my next curly brackets, I will tell Mathematica what I want to solve. And this is pretty nice. Do you see how the colors are changing here as I'm typing these in? So it was bright blue. It says, we haven't done anything with T yet, and it's cleared out. And as I tell it, yes, I want to solve for that. So anything in black is kind of hasn't been defined. Let's go ahead. Okay, so we have our final position and our initial position. So let's put that in here. How do we want to define everything from? So we kind of have to decide where we're going to draw our coordinate system from. So let me go ahead, and I'm just going to, sorry again, I'm drawing with my mouse, so this isn't a perfectly straight line. Let's go ahead, I'm going to call this X and this Y, and I'm going to measure everything from this point right here on the ground. So when I put in my X and Y positions, this will be my starting position is right here, and then my ending position is right here. So I have to make sure that I'm getting in my right starting and ending positions. Okay, so let me update my picture here. As you're calculating stuff, you'll notice that there's these little blocks on the side, and you can actually right-click on these and change the style between text and input. So you can write entire reports in here, but make sure all your calculations are in input. And if you hit enter, it will add new lines. So like I have multiple lines. All of this stuff is contained in just one block. Make sure you didn't accidentally start a new block and then they're not connected to each other. You have to make sure that everything you type in is in just one block of code. And when you're ready to finally evaluate it, you have to hit Shift plus Enter. Shift plus Enter. That will evaluate everything. So that's the other thing to remember. There's just a few things in Mathematica like this you have to get used to, but it is one of the more user-friendly programs out there, which is why I chose to use it for this. Okay, so let's go ahead and plot our starting position. We'll call that 0. So we'll say starting position of 0, and then our ending position is going to be not quite 25, it's going to be 25 minus d, and it's going to be in the negative direction. So that would, I guess, be negative 25 plus, and I called that dd. So it's negative, and we're going to take that into account. Okay, and then our starting y position, so it is not on the ground, and just how I've drawn my coordinate system here. And you can define your datum however you want, but just be consistent through the whole problem. So my starting y position here is 6.8 feet up. And then the final y position is going to be at h. So h is defined up here, so I can say my final y position is h. Okay, so look through this, see if everything is defined correctly. We've got distance, height, gravity with the right units, angle with the right units, starting position, ending position, and then we have our generic constant acceleration equations. The one thing from problem to problem that you'll have to go back and maybe just alter between these generic equations is really keep track of the direction of the velocities, and those you have to look at the picture and figure out what those signs are going to be from the picture. Okay, so evaluating, Shift, Enter, cross your fingers, and we've got squared going on, so we have two answers. We can get rid of this one. You can also, Mathematica is always going to give you these little warning things. You can say ignore that, whether it might use some numerical methods to solve it sometimes instead of analytic, and it tries to tell you, hey, this is how I solved it. But okay, so there is the solution for this. And if we go back to the quiz, let's see, 34, 0.82. 34, 0, yay! Okay, so that's one scenario. Once you have one scenario working, Control C, Control V, you can change around your starting position, change what you're solving for, what you're given. You can change this any number of ways, but once you just get through that first problem, it hopefully won't be too painful to keep chugging through this thing. Okay, please let me know what other problems you'd like to be solved, and I'll make some more videos like this, but you have to let me know specifically which problems you'd like to see solved. We'll see you later.